Thanks everybody for attending this meeting, and of course thanks also for those that are having a look at this in the YouTube channel offline. So today's speaker, I'm very happy to have Claudia Maraston. She's Professor of Astrophysics at the Institute of Cosmology and Gravitation of the University of Portsmouth in the UK. Professor Maraston received her PhD in Bologna, followed by postdoctoral jobs at the Max Planck Institute for Extraterrestrial Physics, MPE, and the University of Oxford, where she held a Marie Curie Fellowship, joining the faculty of Portsmouth University in 2007, and receiving in the same year a Marie Curie Excellence Team grant. She is editor of Monthly Notices, and she is recipient of the 2018 Eddington Medal from the Royal Astronomical Society. So the expertise of Professor Maraston focuses on the development and exploitation of stellar population synthesis models, and she played a very important key role in the analysis of Sloan data in various versions, most importantly BOSS and MANGA data. And we're happy to have her giving us a seminar entitled Probing Stellar Population Models in the Near Infrared with the James Webb Space Telescope. Thanks so much, Claudia. So please go ahead.
Thank you very much, Ignacio. I will have to... Am I still sharing?
I know if you can start sharing.
Apologies, but see what happened. 1 second.
Yeah, sure.
Okay, perfect.
Now, good. Yep.
Yeah. Sorry for this. Yes, first of all, thank you very much to Ignacio for this opportunity. As we will see, this is like the fulfillment of a dream that happened just thanks to this satellite. And the end point of an adventure that started roughly 20 years ago, but I will have the opportunity to describe that. So the spirit of the talk is inserted in the grand framework of studying the formation and evolution of galaxies on cosmological timescales. And this that involves a lot of baryonic physics turned out to be quite a complicated process. And there are a few physics processes that are particularly tricky. The conversion of gas into stars is something that has not yet been understood by first principle and is parameterized in the models and also in decoding the observation. About 15 years ago, it became quite clear that feedback happens not only from stars, but also from massive black holes. In fact, it was a previous student here at the Max Planck Astrophysics in Munich, Darren Crotton, that put out with Kaufman and White the first paper on this. At the same time, we think galaxy mass grow through dark matter merging, but there are, of course, a different type of acceleration and prescription along the cosmic time. And also in recent times, another problem came about that is much discussed in the literature is how to stop star formation, which became famous as quenching. So in part of this variety of problems, there is something that we can exploit, the people thought of exploiting, which is described by robust physics, which is the light of galaxies. So we will now try to understand, exploiting the light of galaxies, what are the main drivers of galaxy evolution. What I want to do in this talk is to refine the interpretative tool to indeed probe this investigation. So, and here in this time, I have to show the beautiful James Webb field that shows galaxies at the distance, various distances, cosmic time, a variety of redshift plus all these arcs. And then in the local universe, we have a more regular array of main species, elliptical, spirals, irregular. So how do we go from there? This is just to give you an introduction. So in order to probe the different mechanisms of galaxy formation evolution, the first thing is to try to extract the physical properties of galaxies. That we usually do by analyzing the light. By properties of galaxy in this context, I would like to mention the stellar ages and formation epoch, the whole formation history, so the star formation history, the chemistry, which is total metallicity, but also detailed element abundance ratio, and also the details on the remnants that are now in the era of gravitational waves, much important, that of course are also processes involving the evolution of stellar populations. The main approach that was pioneered now 50 years ago by Beatrice Tinsley in order to extract the physical properties of galaxies from the spectral energy distribution is called evolutionary population synthesis. Population synthesis is clear. Evolutionary meant at the time to use explicitly stellar evolution calculation and theory in order to describe the properties of stars in various evolutionary phases that are going to be in our galaxy. And here is a non-exhaustive, is a more or less an exhaustive list actually of people busy in trying to calculate this type of models. And to the left, I show Beatrice Tinsley. I'm told you can't see my pointer, but I will point verbally to what I'm saying. In the middle, you see Alvio Renzini, who actually in 1981 defined a theorem in order to conserve the energy of these stellar generations, which was known as the fuel consumption theorem, on which also my models rely. And in the third panel, besides myself, you see Gustavo Brusual, who has calculated models since the 80s that became the benchmark in the literature for population synthesis model. So evolutionary population synthesis is a theoretical framework for calculating the evolutionary properties of galaxies, and these are typically spectra, which is the topic of the IAU managed by Ignacio, or colors, or the mass budget following stellar evolution in order to interpret galaxy data, or also to apply to theoretical galaxy formation simulations in order to obtain an observable spectrum. So just to remind ourselves what we are talking about, this is just a plotting the theoretical CD of stellar population models, here for simplicity for a solar chemical composition running from 1 million year to 10 billion year. We see wavelengths logged in order to compact the scale and the flux. And here there are some labels that help decoding this plot. We see that young stellar population are extremely bright in the ultraviolet, but this ultraviolet, following the short lifetime of massive stars, decrease very rapidly with time, while on the other side of the spectrum, the near infrared, that is dominated by the lower mass component of the population, evolve quite mildly. And so essentially, getting the properties of population, it depends also on what part of the ACD in the data and in the theory we have at disposal. And we'll come back to that. So just as bullet point, the input physics of the models are the energetic and time scales of the stars in various evolutionary phases. And this is usually derived from stellar evolution calculations, but exactly as I will show in this talk, there are certain stellar phases that still elude a complete modeling from the theory point of view. While you have the energetic, in order to match with observations, you need to distribute the energetic into spectral energy distribution that again can be theoretical or empirical according to the phases we are describing. You need to assume an initial mass function, which is the mass distribution of stars at birth, which is a distribution function to run your integral. And we can have a talk just on the initial mass function, which I will skip. Let's consider it as a parameter of the models. And then you would like also in some model, this is done like in my models, to know the function of the remnant distribution. So the stars that end up as white dwarf and neutron stars or black holes in number and mass of that as a function of the age of the stellar population. Very importantly, came out especially in the era of James Webb Space Telescope. There are other effects that you can attack to your stellar population model, and there are people doing that, like assuming a certain fraction of binary system in your population model, or including from the star emission line and nebula continuum. I call them extras, although I have full respect of them because they don't come out directly from stellar evolution tracks, but they need to be followed in an extended manner. Now, it is important to understand also for what we are going to describe in this talk that the stellar population model aims to disclose the physics of population that are not and will never be resolvable into individual stars. I showed to the right, to my right of the screen, a cluster of galaxies redshift about 1, where each blob of light is a galaxy, and there will be no telescope that is able to resolve the individual stars. As a population model aims at exporting the detailed physics of each individual star that could be in your population into an integrated spectrum. What instead people do in our own Milky Way is to know, to see the individual stars as, for example, in the central region of a globular cluster, where you can even distinguish red giants from main sequence turn-off stars. And there you can actually have a direct view of the evolution of the population. But population model means, no, let's go to the hard thing, and let's try to interpret the light of galaxy up to very high redshift. So this is called the integrated light problem, and since the beginning of the development of this model, people thought on how actually to do this integral properly. And so I have to quote something that was very popular many years ago, as you say, but quite interesting. It's called The Pig. It was published by Renzini Buzzone at a conference. And the rationale is that in a stellar population, in a distant galaxy, each evolutionary phase where stars could in principle go through will have an impact on the SED, maybe focused on certain wavelengths, but essentially every bit counts to the total success. And this more or less is the philosophy we pursue in order to try to make good models. And so there are many stars and many subphases, but overall, you can actually define the evolution of stellar population in galaxies in terms of 3 ages, which will have 3 evolutionary phases that are particularly important at that age. And if you could follow this theoretical color magnitude diagram, let me guide you through. Very young population with ages lower than 100 million years, besides stars at the main sequence, will profit from the energetic of helium-burning stars and their phases of massive stars. On the other hand, we also know that all the populations, so those generally older than 2 to 3 billions of years, have the light dominated by red giant branch stars besides the main sequence. The part in between, so between a few 100 million years and a couple of billion years, peaking at 1 gigayear, is called the intermediate age of galaxies. And then the most important evolutionary phase, evolved phase in Portsmouth sequence, is the asymptotic giant branch, so AGB. And I say this in advance, this will be a main protagonist of this talk. In fact, the asymptotic giant branch, and in particular the part of it that is thermally pulsating, and I will briefly explain you what it is, was always felt as the big elephant in the room of this evolutionary population synthesis, for the reasons that I'm going to explain. Here I depicted a color magnitude diagram with all the evolutionary phases of a globular clusters, actually, a typical globular cluster. So the asymptotic giant branch is the most luminous and last most luminous phase of the evolution of intermediate mass stars. And as you see from the colors, it occurs at very low temperature, but also very high luminosity. So it was always felt that this phase is in principle very important, but because it's short, evolutionary tracks have had difficulty to full model the duration of this phase, especially because this phase is affected by strong mass loss. So in essence, it was always difficult to calculate a full self-consistent evolutionary track for the thermally pulsing RGB, and I would like to acknowledge the extensive work by Paola Marigo over the year, and acknowledge her work especially because unfortunately she passed away last year. And Paola has calculated a huge amount of tracks from the Padova group in which she followed specifically this evolutionary phase. I will be able later to describe also these models. An extensive review was given by Iberner and Renzini in the 80s, explaining how the problem of mass loss is a severe one, because in essence, we don't know where to stop the evolution of the stars. And that's why we need to resort to data to actually calibrate and test our stellar models. So for this particular phase, two of the input physics that I told you earlier are needed for evolutionary population synthesis, namely the energetic and also the stellar spectra, are extremely uncertain. And in fact, you would like to look at how spectra for stars in this specific phase look like, and they look like different from any other type of spectral energy distribution. In these two plots, due to the work of Lanson and Wood and Lanson and Musin, I show a run of carbon-rich observed spectra to the left, and you see the blue is the hottest and the red is the coldest. You see that the continuum is featured by deep, sharp edges and absorption due to carbon feature. To the right, you see the other species, the other stellar species on this phase, which is called oxygen-rich, which again, I show a warm type and a cold type. And the cold type especially has these bands that are CO and titanium oxide that again eaten up most of the continuum, but are quite distinctive. These are empirical data of 20 years ago, but very recently we actually used a modern spectral library to find this, to feature this type of stellar evolution. And you see again in this plot that is a high resolution and better signal to noise, how sharp are the carbon, nitrogen, and C2 and so on features that are actually also visible in the optical up to 1 micron and not only in the near infrared. So why is this important? Because in principle, as we will show that, if you could find signature of this type of stars in a distant galaxy, well, you could recognize them from this very peculiar spectra, and you would have an immediate link to certain physical properties, especially the age of the galaxy. This just to give the link between individual stars and distant galaxies. As I said, this is probably the stellar phase that has been more discussed in the literature over the past 20 years. Starting from, in fact, my PhD thesis, which marks as the first attempt to include the stellar phases into evolutionary population synthesis. So I want to summarize all these years of work by points. And there are points of consensus and points where we disagree. So I think we all agree that the asymptotic giant branch internally pulsating is harder to be modeled fully theoretically because of the unknown mass loss, and also that we need to calibrate our theoretical energetic with data if that is possible. But then we disagree, or different groups disagree on how to perform these calibrations. What I put forward back in 98, and this was also reprised by Conroy and Gang, is to use individual ages of stellar clusters in the Magellanic Clouds, which happen to be very rich in these stars due to their age. But other groups like Brusoil and Chalot and the Padova group decided, instead of using clusters, to use the population of field asymptotic giant branch carbon-oxygen stars. It's two different philosophy, because essentially you ask your model to determine the age of onset of this phase in the first case, or to constrain the star formation history of the model. Let me show you, first of all, what it means. In this plot, you see in the y-axis the bolometric contribution of the phase over the total bolometric of a stellar population as a function of the age of the population. Let's look at the extreme first. Young population with log age about 8, which is a few hundred of million years, have a very little contribution by this phase, for reasons that are well understood in stellar evolution. All the populations similarly have a low contribution, and there is this distinct period that tip around the 1 billion year, in which instead real clusters display a contribution that is about 40% in the bolometric. These are actual data. In the Magellanic Clouds, group in age bins, and the curve is what I calculated at the time to explain this asymptotic giant branch phase transition in stellar population. Is essentially the mark, the divide between young population and old population. So if you then calculate the total energetic of the stellar phase, and I'm showing a plot that does that, where all the stellar phases are signed with their acronym. I'm sorry for the acronym, but I hope they are known, but let me guide you briefly through. Solid is the main sequence, dotted is the subgiant branch, dashed is the red giant branch, long dash the horizontal branch or helium burning, and then the asymptotic giant branch as this dot dashed. As I said, you do the evolutionary synthesis model completely, and with my formulation of the asymptotic giant branch, you find this nice 40% contribution at ages around 1 billion year. I want to show very briefly a similar plot published for the Brusual shallow model, where indeed you see this in the upper plot. There is a contribution by the asymptotic giant branch, but the one of the main sequence is higher. This is important because it is actually implies differences in the predicted spectral energy distribution. So the whole case, I say 20 years ago, and you will see that is exactly that, started with the plot that I published in 2005, where thanks to the spectra, to the empirical spectra of Lanson and Wood, I was able to translate my calibration of the energetic into stellar population spectral energy distribution for population model. Here, just as an example, you see how a simple stellar population, just a single burst for simplicity of 1 gigayear of age, looks like when the stellar phase is included. This is the solid red lines. If you remember the bumps that you have seen in the stellar spectra, well, they get transported in the total integrated population spectrum. I also did the exercise of subtracting or not including on purpose the stellar phase, and you have the lower red line, where due to the lack of this stellar phase, the spectrum is quite smooth, there are no features, and there is also less near-infrared flux. Now, at the time, 20 years ago, I also plotted what were the available model, the most discussed models of population, by Brusual and Charlot 2003, by Pegase, Fioc and Rocker, Volmerage 97, and Starburst 99, which are those black lines. And it was immediately evident that the models were vastly different, especially long-word 5,000 angstrom all along the K-band. So basically, from the visual to the near-infrared. And by comparison, I concluded that the difference was the different treatment of this important but peculiar at the same time stellar phase. Now, assuming that this model were more or less correct or fair, now I want to emphasize the type of molecules that you would see in the spectra of a distant galaxy if you would able to get the data that have actually this interesting age range. And you see carbon-nitrogen spectra, those edges present all along up to 1 micron, titanium oxide, the C2 molecule, H2O, so water and carbon oxygen. And these were just an extract, there are others. So the prediction was, you should see strong near-infrared absorption of carbon and oxygen-rich species, and in this way you could unequivocally associate this absorption to the presence of TPAGB stars, and therefore the age of your galaxy would be around 1 billion years. This absorption, on the other hand, there is a theoretical explanation why you would only see during this phase, because they appear due to convective dredge ups that are stellar evolution events that happen during the pulsation, and especially at low temperature. So when the model were published, there were initial comparison with data, and especially tire redshift, and I will have the chance to explain that. And this was the work that immediately made the comparison between the two classical model. Brusol and Chalot is featured in red here, and my model are blue. And by merging data from HST, the first 3 points in the optical, and the Spitzer satellite that was launched in this year, you can get the full SCD, photometry SCD, of galaxies. And this is galaxy ratio 1 from the optical to the near infrared. And you see that a simple fit shows that, in fact, the near infrared point of this galaxy were quite high. And even if, of course, they clearly favor a high flux like found in my model around the edge where this phase is important. We were discussing just the other day this photometry of redshift galaxies. Roughly at the same time, this paper of a student of Guinevere Kaufman and others look at photometry at redshift 0, and the sample of galaxies that were hosting young population were finding actually similar effect. But obviously there were also discrepant results. And in particular, two works stand in confrontation, so to say. And let me first speak about the work that is based on spectroscopic redshift. This is by Cimatti 2008. And they have the G-mass spectra. Apologies for the label. I hope you can read that of redshift 2 galaxies with very high near-infrared flux and clearly favoring strong TPAGP models. At the same time, Mariska Kriek and collaborators collected a huge sample of galaxies, but based on photometry redshift, and also with the priors on the star formation history. They were selected anyway. Please do see the detail in the paper. They concluded exactly the opposite, that the TPAGP in galaxy is weak and the Brusol and Chalot model fit the data better than my models. So there was a very lively debate still ongoing up to last year. So there has been a revision of models, and now these are also very important that I want to report now. So I just recall my calibration, which sees a peak age around 1 billion year, based, of course, on globular cluster ages and data at the time of my PhD thesis. Charlie Conroy revised this plot and concluded for a much later peak ages around 3 billion year, but especially for a much lower contribution of this stellar phase, and concluding that, in fact, my model overestimated the contribution of this phase. That's so in science, you have, when you put something forward that, in fact, was not looked before, then you get confirmation, but you get also discrepant results. And so we proceed. And so the way we proceeded was to take a look at the models and my models, and to use more up-to-date ages for globular clusters, just to acknowledge this work in the literature by Conroy and collaborator. So in this paper 2013, I calculated another series of models, which I called them 13 just because of the year where we put them forward in this paper. And I recalculated, these are the golden line in this color age plot, mimicking the one that was published by Conroy. And the data that we used are the red points. And the conclusion is we still find a peak age around 1 billion year. We could not confirm a peak age of 3 billion year as was put forward. But what we found with the new ages of globular cluster, that the onset age of this evolutionary phase is roughly 0.6 billion year, which is somewhat older than what I assumed back in 98, which is interesting. That is due to, in fact, new calibration of ages of globular clusters. And so, in a sense, in this model, I have changed the fuel consumption to make it more adequate to the average of this data, but also change the onset age, and we'll see what happened. So you see a lot of work, but until last year, I think the community had little idea on how the spectra, the near-infrared spectrum of a 1 giga-year-old galaxy would look like, because it could look strong in this feature as my model would predict, even the revised one, or very light in this feature as the other model decided. So this is roughly a 20-year-old debate. And we thought, and we were hoping, well, the data will tell us at some point when the near-infrared spectrum of a massive galaxy will actually be available. This beauty happened last year, and is published in this Nature Astronomy paper. And I would like to acknowledge that the person who found this galaxy spectra in the James Webb Space Telescope archival are Emanuele Daddi, my long-term collaboration, and he's a PhD student, Xin Lu, who actually have led the paper. So essentially, what I'm going to show you now is the full spectrum, high signal to noise, beautiful spectrum detected by James Webb Space Telescope that we analyze for different models. And as you can guess from the title, what we found is strong asymptotic giant branch features in this very distant 10 billion years in the past galaxy. So this is the spectrum, and those of you, but I think most of you in this call that are passionate with the spectral energy distribution will appreciate that this is a unique spectrum that nature is showing us actually. So you see the flux as a function of the observed wavelengths at the redshift, rest framed with the accurate redshift in the upper panel. So we do have the spectrum from the B-band optical all along the K-band. And what you see here is, well, a lot of features, many more that we could even think about. They all have been identified by Xin Lu, and there are also, this is probably the first time zirconium oxide is seen in a galaxy spectra at all. So you see a lot of carbon, nitrogen, titanium oxide, and CO. And this is qualitatively really resembling of the effect of a TPGB stars in model spectra as I modeled 20 years ago. So important to note that this galaxy, because it's very bright, it was a filler in the James Webb Space Telescope archive. So essentially we used data that we didn't take. It was very cheap. And the signal to noise of the spectrum is 100. I don't know if you can distinguish it, but the distance between the two lines in the spectrum is actually the error on the spectrum. So this is a super demanding data set for models. So obviously at first glance we thought, okay, we found it, but let us be a bit more quantitative. Here we compare the spectra to observe the carbon stars to the left and observe oxygen-rich star to the right to be guided by the identification, because these are ratio 1 objects. So you are actually quite redshifted, and you need to make sure that the features are the same as they observe in the lab. So anyway, there is a full identification of feature, and they all seem to correspond to the actual stellar features. But then obviously we also made a comparison with population model, because that was the scope of the whole work. And let me just briefly comment on these two plots. To the left-hand side, we make a comparison, yet not a quantitative, a qualitative comparison to models with sizable TPGB, which are my models 2005. Oh, I messed up with the colors. So the model 2005 are the green, actually, which display most of the features. And the revision is blue, which still display many features. And then to the right, these are models with weak or poor TPGB. I didn't give this model this name, but others in the literature, and we have used them. So BCO3 in yellow display just a couple of features, and the Conroy model, again, just a couple of features, 2 to 3 features. due to the very weak energetic in this specific stellar phase. Now you want to do the chi-square, and I will tell you chi-square is actually has a very high value because these are incredibly detailed data that we want to model, but there is a clear signal. So we could reach a minimum chi-square, very high still, but minimum with this model. So my revision of the TPGB. The TPGB poor are pretty much excluded by the data. My initial 2005 model, that's very interesting because in terms of features, it has the best success, but the high chi-square here is due to the star formation history. So we think that's due to the onset of the phase. So it's a different problem, which maybe has to do with the star formation history of the galaxy, but this is also an interesting result because it could help us constraining stellar evolution, not only galaxy evolution. So this was a clear result. We explored many other models in the literature, like the widely used EMILES that cover the near infrared, an unpublished version of Bruce Echelon model that our referee asked to plot that published in 2016, and several others. But there was no success in all of these models. And this included the latest X-shooter-based models published in 2022. I want to spend a word on these models for the reason that these models have fully empirical stellar spectra, although it is unclear whether they actually include the carbon-oxygen stars in the amount that is needed, but it's fully empirical. But the treatment of TPAGB followed this initial calibration on the star formation history that I mentioned by this group, and the latest Padova tracks that are called Colibri. And this gives one of the worst chi-squares. So that's very important because in reality, you notice that to fit the galaxy spectra, you really have to master the energetic and to have adequate stellar spectra, and this is the conjunction of the two. So in reality, our results are very robust with respect to these models. To all these models.
Can I ask a question? Is it possible to ask questions? Or
Uh,
not? Are you tight on time?
Yeah, it's free. You can, yeah, please go ahead. That's fine.
Okay, yeah. So if you could go one slide back, what are
Yeah.
the gray, the gray stripes there? What are they representing?
Yes, no, that's very good. This is something observational that has to do with this X-shooter instrument that the student included. Ali, apologies, I don't know the exact detail. But this is probably where the spectra have been merged. So this instrument, X-shooter, allows a coverage of visual up to the near infrared, but it exploits two different branches. So it's probably only showing that.
Okay.
Okay, sorry if I was. I should look at the paper, at my own paper to understand. I don't think they are very important in this for these conclusions, but possibly in the caption it is written why they are highlighted. And
Yeah, if I may say, this is mainly because you're observing from the ground. I mean, you have James Webb data that you have full coverage, whereas from the ground you have regions where you can observe and some regions that are actually dodgy in a way, so you cannot. And I think that's the blocking. I don't know. We have to look
possibly,
at the
yes.
details.
Yeah. Mhm. But still, the models they calculate are continuous, you see, also over this region, because there is been, of course, some interpolation of the spectrum. Yeah. Okay, if I answer your question, I should probably carry on.
Yeah, thanks.
Yeah, please go ahead.
Of course. So I mentioned at the beginning that the holy grail for this type of modeling is redshift galaxies, and we put forward this back in 2004, but our first proposal to Spitzer was rejected due to the original nature of the models that we were using. So interesting. We had to wait 20 years, but this is just my comment. Why are redshift galaxies? Well, let's follow stellar evolution as a function of cosmic time, which is what this plot is showing. So this is age translated in redshift for two different formation redshift of 5 and the other one is a much higher redshift. So the first transition in stellar population will involve very massive stars, as I said, OB, and they will have their own stellar evolution importance, OB stars, red supergiant, and Wolf-Rayet. This happens at a very, very high redshift. While the population evolves, it becomes intermediate age, and we want this 1 billion year. 1 billion year, depending on the formation of galaxy, of course, may happen at redshift 1 to 3. That, of course, depends on the stellar evolution. Then the population ages, and on cosmological timescale, the redshift below 1, you find the red giant branch dominating the light. So, of course, there are star-forming galaxies in the local universe. Star formation is everywhere. However, to find the signature of a short phase, you would like to have all the stars in your galaxy, or most of them, going in synchronous in this phase. And this happens particularly in galaxies that form their stars quite quickly. And that's why Emanuele Daddi, when scanning in the catalog of the James Webb, was looking for galaxies that were quite quiescent and massive. And why? Based on paper like our own of 20 years ago, we think the most massive galaxy form quite quickly at high redshift on short time scale. And this means the stellar evolution is really clear in this galaxy because most of the stars will go through the phases. Apologies, at the same time, emphasizing the signal of very short evolutionary phases. As I said, this is an ongoing work and for many people of many years. Why do they matter in galaxy evolution? Well, it was demonstrated that models with a TPAGB, sizable TPAGB phase, become redder at a younger age, and this implies lower mass to light ratio and usually lower stellar masses. So, galaxies, the analysis of galaxies is made with population model. You don't know the galaxy property before you put a model on it. And so it turned out that if these models are correct, your galaxies are younger and lighter, which was shown also in this paper 2016. The other advantage is to break the age metallicity degeneracy. To all of us working with spectra, we know, as Guy Worthy put it forward, that the optical range, so up to roughly 1 micron, does not allow you very well to distinguish a metal-rich young burst from a less metal-rich but older. And there you see the equivalence 2 gigayear versus 8 gigayear, twice the solar metallicity versus solar metallicity. In my paper, I revised that, say that's correct, but if you're able to get the near-infrared res frame, then the 2 billion year population will have near-infrared flux due to the TPAGB, and the other will not. So, a lot of advantages. Where do we go from there? In our Nature paper, we had 3 galaxies, of which one with extremely high signal-to-noise. We have been awarded more James Webb Space Telescope time, and we got roughly 60 galaxies. And I'm happy to tell you that all the new data confirm our results. And Xin Lu is writing up the paper, but we agreed to show these plots. So just 3 plots, and then I will go to the conclusion. So here I plot the sort of time scale of star formation, sort of age of galaxy as a function of the galaxy obtained with the best fitting model. So this is approximation. Red points pertain to the fit obtained with BCO3, Brusel and Charlotte 2003, and blue with Conroy and Gunn 2009. And what you see here is that the model with TPAGB, what I was exactly saying, generally tend to get lower ages, while the other model tend to go to very high ages. Note that these are high redshift galaxies, so some of these ages are barely within the age of the universe at that redshift. You don't see this here directly because it's not a redshift plot, but we will have it in the paper. As a consequence of a younger age and the decrease of mass to light ratio, the stellar masses that are derived with the M13 model are 0.5, 0.3, 0.2 to 0.5 DAX lower, something that you see in this scale. Apologies for the plot that I was sent is a bit faded, but all of this happen with a better chi-square from this model. So this is quite convincing. It happened essentially for all galaxies, and we concluded that galaxies become younger, lighter, with a better fitted spectrum. This has an impact on cosmology, and this is my light slide. This is a bit pushy, but we will see what we have. Since a couple of years, since the results of James Webb Space Telescope were published, we have a lot of debate on the impossible galaxy that don't live in a lambda CDM universe. And the reason is that they are old, they are massive, they are far too bright, and so they violate what is the available baryons at certain redshift. I don't want to enter in a lot of detail, but this is the stellar mass density as calculated, assuming certain cosmological calculation, and the efficiency of star formation when epsilon is 100% efficiency, and this is 10% efficiency. This is Boylan, Colchin et al. And you see that, in fact, the observed point as a function of the stellar mass are actually requiring 100% baryon conversion, which is quite not realistic, and also the error bar outside. But I noticed that they don't put an error on the stellar mass, so sorry, I did it. So in principle, the error should go this way. If we are to reobtain ages of galaxies across cosmic time, the tendency is to get younger and lighter ages, and so this discrepancy could be reduced. And this, I think, is an analysis that we need. In fact, we are already starting doing, and it's very important to understand in which cosmological model we all live. And this concludes my talk. Very briefly, the summary is that for the first time, we detected, so it was detected, thanks to the James Webb Space Telescope, a strong feature that have to be associated to a sizable thermally passing asymptotic giant branch phase in the galaxy at the time. The galaxy, in fact, with this model are around 0.7, 0.8 billion years old, and you see really important species that have not been seen before in a redshift between 1 and 2. Now with the new data, we go up to 3. This allowed us to really nail down the contribution of this phase in population synthesis model that has been discussed for 2 decades. And we found that, in fact, the best fitting model is the revision of my models displaying sizable TPGB, but with an onset time of 0.6 giga-year, which we are going to probe with more data. I associate 0.6 giga-year to the typical turn of mass there. We also noticed that the lighter TPGB is disfavored by data, or TPGB from these calculations, which casted out on, on ages and stellar masses that have been used based on this calculation, which have been used for both galaxy evolution but also cosmology purposes. Besides that, there will be an impact on chemical evolution and dust production. The TPGB is the strongest dust production, especially at high redshift, because supernova also destroy the dust, and this is also something that people started to work. I'm very interested in the aging of a galaxy across cosmic time, because stellar evolution gives you an independent time scale from cosmology, so galaxies, cosmic chronometers, and well, we hope to actually get robust ages from now on, at least from the point of view of these phases. So thank you very much for the attention, and I'm open for questions.
Thanks so much, Claudia. Great stuff. I mean, it's the data are really, really amazing. I mean, just to think about it, that it's a filler, it's quite a thing. So, I mean, this is really interesting stuff. So, any questions from the audience? While you're waiting for thinking about your question, I'm going to skip us having the president's favor in a way. So you showed this really nice data, and then you're comparing them with other models. But I had the feeling that there was a mismatch in the continuum. So, I mean, I was wondering, did you look into that because this is present data? I don't know whether the flux calibration is up to scratch, whether you're considering like fitting continuum subtracted data, or even going into line strength. So, what's your feeling on that?
Fantastic. So first of all, I should give the merit of all the fitting to Xing Lu and Raphael Gobat, who have done the fitting. I was invited to the paper after the result that was fine to make the interpretation. So yes, we have discussed calibrations, and there are James Webb expert people on the paper. Data calibration is an issue. Xing has performed the fit with different calibration, and by and large, the conclusions are the same. We looked at certain line strengths, as you suggested, especially, this is all in the paper, in the extended material, and the line strengths give an even stronger response towards the best model than the continuum, probably for what you noticed. We did the full SED fit because this is what people do in the literature, and we wanted to actually replicate their type of analysis. With the three models that usually are used, but much more BCO3 and Coroi, they are milder resolution models. So they are going to have some mismatching in certain places. In fact, what we are doing now, besides having also used our new data to get our result based on three galaxies are robust, based on many more, we are also working on the models because there is, I mean, besides matching most of the feature, there are some interesting mismatches in some features that may indicate carbon enhancement, for example. This is what we are mostly looking at. But I agree with you, Ignazio. For a high-Rashi spectrum, you need to look at the continuum, you need to look at the feature, you need to look at the calibration.
Thanks. Yeah, that's amazing stuff. So, Winnever has a question. Please go ahead. If you could also open your camera. I don't know whether you have
My
a
camera is, yeah, unfortunately
No worries.
broken. I have an external camera, but I didn't connect it. It's a bit strange.
worries.
I'm just down the hall here from Claudia. So that's beautiful to see those JWST spectrum with so many different features and so on. But at the beginning of your talk, I noticed you also said that these features were detectable between 8,000 angstroms and 1 micron. And in terms of galaxy statistics and getting large numbers of objects, there's lots of post-starburst galaxies that you could select from optical surveys and perhaps from the H-band surveys like PFS. So what do you think you could get from if you just had the smaller wavelength range? Is there useful information there?
Yes, I think there is, Guinevere. I think there is, because it is true that, of course, also the near infrared in itself help you to constrain the star formation history. But all these titanium oxide and CN bands are also visible here, and I showed them in the carbon stars of master, if you allow me to go back. This is the master wavelength range up to 1 micron, and you see how these spectra are actually visible. So I think, in fact, I mean, you use also the UKIDs, but some people look at the optical. The contribution is lower, the level of flux is lower, so you need to have very good data, signal to noise data, and especially post-starburst in the right age range. But I think it is possible, and this feature should be visible also there.
Because I have occasionally seen it, and I actually thought it was background subtraction errors, but maybe it's actually real. So it would be interesting to take.
It's actually real. I mean, you see that for the James Webb spectra, we have all data. Yeah, so the rest frame wavelengths is from 0.4 for 1,000 to 1 micron. You already see a lot of feature that you can't associate to other type of stellar evolution. And in fact, there was a paper by the Creek group with this fire and spider, this very redshift post-starburst spectra. That when they said that in fact they have difficulties fitting these models, this spectra with the prospector and Coroi models, possibly due to evolved stars, which I think is the same problem. Yes, so yeah, fun times ahead, possibly. Thank you, Kina.
Thanks.
So I was wondering, Claudia, what do you make then of the results that were presented by Crick and other spectra where basically no features? I mean, what happens? Is it gets more complicated? Maybe when you're going to lower redshift, you end up getting a more complicated stellar population.
Yes, so in fact, what I make now it's hard. One would needed to take a look. And let me tell you what I think. So the main difference between these two works was the Chmat et al. Was spectroscopic redshift, and they were fitted the three models. The green one was a model by Charlot and Brusoil 2007, developed in order to increase the TPAGB, as you noticed, but without feature. And this was done in a non-parametric way, so the fit was free to choose the particular age of the particular model. Now, in this work that obviously was done in a statistical way, and they had a lot of galaxies, but as you said, the galaxy span a certain redshift, and the prior was that this was a post-starburst and photo Z. But both were actually based on BCO3 models. So, what type of systematic this may trigger remains unknown. In fact, in their paper, there is also a section in which they said that, however, proceeding towards higher redshift, the Maraston model fit better and better the SED. So there might be exactly what you said, a sort of confusion of on the galaxy classification and star formation history going towards lower redshift, plus a small but maybe irrelevant in this case effect of the photo Z that were determined with the specific models. Other than that, Ignazio, the only thing I could tell you is that it would be great to have the spectra of the same galaxies and see how they look like now.
Indeed.
And I bet that James Webb is going to tell us. There was another work at the time that I didn't mention, but now we know about it by Zibetti et al. They took the spectrum. Yeah? I wanted to tell you, this was already explained by Riffel et al. 2015. The galaxy had a weak post-starburst, but especially the data had nowhere sufficient signal to noise and resolution to display any feature.
Okay.
So again, there it would be interesting to get the same galaxy to get a better spectrum. And I agree with you. Yeah.
I mean, the thing is, that's why in a way this was a prediction you made, and it's 20 years because you have to wait for James Webb actually to have data with enough quality, perhaps to
yes.
yeah.
But now the quality is larger than the models.
So Danny has a question.
Yeah, mille grazie, Claudia. Very nice. Maybe you've already answered it. I'm just curious, what's your main next challenge you're working on?
No. Okay. In this realm, I would like to understand this absorption also in terms of abundance ratio, because these are massive galaxies. I can tell you, I don't think this will make a major role unless we look at the carbon. So I don't think alpha enhancement will affect that. We are already working with theoretical spectra and seems to go this way. But the carbon enhancement may actually emphasize certain features. So we would like to make a chemical evolution. We started in the optical, with our flex model with element abundance ratio. This galaxy may be 0.3, 0.2 DAX alpha enhancement. We want to do the same things in the near infrared. This is the main thing. But the second is to get the robust stages and to revise the cosmic chronometer approach using James Webb Space Telescope if possible. I don't know if this answers your question.
Sì, grazie.
Prego.
So are there any other questions? Okay, if not, we will finish there. But that was really amazing data. I mean, this is really, as you say, waiting for so many years and finally beginning to see high quality spectra that you can play with. So I'm eagerly looking forward to all your papers on this topic. Really looking forward to it. Thanks so much, Claudia.
Thank you very much, Ignazio, and thank you everyone for listening.
Thank you. Thanks everybody. Yeah. Take care. Bye bye.